Any questions from last time? Was the class so far? Okay, I'll just continue the review of classical optics because we want to discuss something important that has some bearing on quantum optics in this class. So we'll just go through this pretty quick. So in the last class, so this is Maxwell's wave equation that we introduced. And from this comes many of the consequences of optics and interference and so on. So we showed that in the vacuum or in a medium, some dielectric constant epsilon r, that the electric field will obey this equation. So that is EM waves with the speed V equals 1 over square root epsilon r times c, which is also c over n, where n is the refractive index given by square root of epsilon. From this, we can also from the Maxwell equations, we know that the electric field and the magnetic field and the k vector form a triad mutually perpendicular to each other. So this is the x-axis, y and z. Then this is ex, vy, k is along the z direction with magnitude k equals 2 pi over lambda. Then again, then we know that the solutions of the wave equation will be of this form. And similarly, there will be a similar equation for Vy. So Ex0 here is the amplitude of the wave, and phi here is the optical phase. So any classical wave then is defined by its amplitude and its phase, in addition, of course, to the wave vector and omega, the frequency. So as we will see when we get into the quantum optics, we want to be able to come up with appropriate operators or equivalents to these two quantities, the amplitude and the optical phase, and we'll see what those might look like when we get to the quantized field version of this. So just to continue or finish up the definition, which you all know, k, which is the wave vector, goes as 2 pi over lambda in the medium, which is also equivalent to the angular frequency omega divided by the velocity of the in the medium, which can also be written as m omega over c. Also, from using the Maxwell equations, not the wave equation, but the individual Maxwell equation, you can show that the amplitude of Vy naught and Ex naught must be related to each other. Okay? So essentially, if you start with del cross E equals minus dou B over dou T, this implies that dou Ex over dou Z equals minus dou By over dou T. And similarly, from del cross H equals dou D over dou T, we get another equation which is minus dou By over dou z is equal to mu naught epsilon r times dou E x over dou t. From this, we can show, if we substitute in now these expressions for E and V, you will find that the h y naught, which is just by naught divided by mu naught, is equal to Ex naught divided by z, where z or z naught where z is defined as the wave impedance mu naught divided by epsilon naught. Okay. And in free space, z naught, which is the wave impedance, you can see it has the form of an impedance. In a minute I'll explain, because of course you can check it from the dimensions, but in free space, when epsilon r equals 1, this has a value of 377 ohms. You can see that this must have the form of an impedance. If we remember from Ampere's law, H dot dl equals mu naught I, right, a current. So we see that the loop integral of H naught over some boundary is going to be proportional to sort of like a current flowing in the surface, crossing that surface in the boundary. And similarly, you can do the same thing for Ex naught, right? That will give you the potential, right? And so we see that the potential across the surface is related to the current in this formula by the impedance. So the current equals the voltage divided by the resistance over here, which is C. So this will be useful, especially when you consider some things like matching of impedance between two different media. For example, we can rewrite all of Fresnel's equations. If you remember Fresnel formula for reflection of an electromagnetic wave at a dielectric interface, you can rewrite all that in terms of an impedance matching between boundary 1 and boundary 2. This will also be useful, for example, when you deal with microwaves and you're dealing with many different types of devices like coplanar waveguides, strip lines, etc. So it's just another way of recasting some of the expressions or thinking about some of the formulas for wave transfer across different media. So the next important part, of course, is we want to understand the energy flow in the wave, right? So that's what the wave does. It takes energy from one location to another. And for that, we define the pointing vector, which is equal to the power per unit area, and it is also equivalent to the intensity. So the pointing vector is defined as E cross H, and I'm sort of skipping a lot of subtleties here about it has to be normal to the surface and so on if you want to actually define the value of the intensity. But just for for this review, all you need to remember is that the time average of the pointing vector will then be given by 1 over z times E of t squared RMS value, which can then be written as 1 over 2 C epsilon naught and Ex naught squared. Okay. So we see that the energy that is flowing, or the power per unit area that's flowing in the wave, is proportional to the square of the amplitude, and this has consequences. For example, when you think about the detection of a intensity of the wave or the power in the wave on a detector, you're going to be immediately susceptible to or sensitive to Ex naught squared and not Ex not directly in most situations, okay? Unless you do some kind of phase sensitive detection. The next aspect that we will consider, which will come up a lot, especially when we consider quantum information processing with photons, is the polarization of the light wave. Okay. Again, I'm not going to go into details here, but just to remind you that essentially the idea is that when you look into this light beam, so here's a light beam propagating to the right here, and you look into this light beam, then this vector Ex can have different states. I mean, we know that E has to be perpendicular to this K vector, but it doesn't necessarily only have to oscillate along the X direction or the Y direction. For example, it could oscillate in the at a diagonal angle, for example, right, or at any angle, really. So that would be called linear polarization, right? And so looking into the beam from the Z direction, if I were to plot the X and Y axes and then look at the vector E, the vector E would be, say, at some angle theta with respect to the Y axis, and that would be a linearly polarized wave. Okay, and then you could have circularly polarized, and that can be thought of as a combination of two waves, which is one wave which is oscillating along the X direction and another which is oscillating along the Y direction with a 90-degree phase shift between them. And so if you look at that wave, you get a circularly polarized light field, and this is right circularly polarized because it's flowing clockwise as I look into the beam. And so if you can see, then there will be a left circularly polarized, which is counterclockwise. And in this case, the amplitudes, even though I didn't draw it quite very well, but this amplitudes Ex naught and Ey naught must be equal to each other. So those are equal. So this is Ex naught equals Ey naught, and phase shift between the X and Y axis, delta phi, which is pi over 2. Okay, that's the circular polarized. Or if it's minus pi over 2, then it's the left circularly polarized. And of course, we can also have elliptical polarized. And now Ex naught is not equal to Ey naught. The phase shift is still 90 degrees. Okay, so and why do we care about this? Well, as you'll see, when we talk about quantum information processing, the states of polarization define a orthonormal basis in this Hilbert space, which can be used, for example, to construct qubits, right? Quantum bits which have some information stored in them. And so a typical information state might be, say, horizontal polarized and vertical polarized. They would be called as the 0 and the 1 basis of the qubit, and then you could make transformations between 0 and 1, for example, using polarizers and rotators. Or if you define the qubit as a 0 for a right circular polarized and 1 for a left circularly polarized, then by using quarter-wave plates and so on, you can transform between these two qubit degrees of freedom. So for example, one of the important components would be a polarizing beam splitter, right? So polarizing beam splitter then works like this. You have some electric field which is say diagonal, like in this state, and then when it comes into this polarizing beam splitter, it comes out polarized in this direction, that is horizontal direction, or in the vertical direction will be split in that way, and this is carried out through the effects of birefringent crystals such as calcite or quartz, which have different refractive indices for different polarizations. Okay, and that's what allows these to, sorry, that wasn't clear, this is making an angle theta in the xy plane perpendicular to the beam, and then it comes out with say horizontal polarized and vertical polarized over here, which is proportional to say the cosine of the angle or the sine of the angle. Okay, so this allows us, for example, then to detect how much, so this would be a superposition in the qubit basis, right? It would have some component along the vertical, some component along the horizontal. We'll introduce all these ideas more formally, but it's pretty clear. Hopefully now you can determine how much of the wave function for the single photon is along, say, one basis, say the vertical, and how much of the wave function is along the other basis, the horizontal. And this allows you to essentially measure or project the qubit into one or the other basis, right? So that's why photonic quantum information processing was very rapidly adopted, because it was very simple to measure the qubits and manipulate the qubits using these simple linear optical devices. Okay, now we'll come to sort of the beginnings of understanding coherence and correlation functions in optics. So we are going to start with the simplest correlation function. So to introduce that simple correlation function, let me first remind you about interference and diffraction. So the essential idea is that you take a slit, right, and you send in a plane wave. Okay. And then what happens is that the wave spreads out after it hits this slit. Let the width of the slit be d, and then we observe far out here on some screen, which is a distance L away from the slit, we observe some kind of interference pattern or pattern. Okay. So if you look at what's happening to the intensity pattern or the electric field at the screen, we can identify two limits. Does anyone remember what these two limits are called for diffraction at a slit? There are sort of two regimes in which we can calculate the electric field on the screen far away. Does anyone remember those regimes? I don't know if you've had optics in your undergraduate so far, but has anyone studied diffraction and so on? Do you remember this? They both begin with F, if that helps. Fraunhofer and Fresnel, right. So there are two limits, or two regimes where we can easily solve, not easily, but at least we can solve the electric field at the screen. One is called the Fraunhofer limit, and that is governed by the slit distance, or sorry, the screen distance from the slit has to be greater than, much greater than, a quantity which is called d squared over lambda, which is called the Fresnel number, or the Fresnel zone number of the slit. But anyway, so the point is that when L is in this very large distance regime, which can be achieved, for example, even with lenses and so on, but I won't get into that trickiness that we do with optics. The point is that when L is very large, essentially say infinity, then basically this is called the Fraunhofer or far field limit. Okay? And then in the Fresnel limit, the near field limit, so this is far field, okay, then L is lesser than or equal to d squared. Okay? And in this class, we'll mostly just be considering the Fraunhofer limit, because it has a nice interpretation for what's happening to the wave as it diffracts. You'll see in just a second. So the electric field at the screen now in the Fraunhofer limit is given by this formula. Well, I'm not writing all the parts of this formula, but basically it's just an integral from minus d over 2 to d over 2 exponential minus I k x sine theta dx. And x here is a coordinate along the screen direction. So this is x, and then z might be propagating to the right. So if you look at this formula, you can see immediately again an analogy. This is equivalent to integrating from minus infinity to infinity. Okay, some function which we'll call, say, the slit function. Let's call that, say, slit function of x times e to the minus I kx sine theta dx. Okay? And so again, hopefully, where s of x represents the slit function, which is essentially 0 outside of these two regimes, and between minus d over 2 to d over 2 has a value 1, right? So it's just a box function, right? And so if I call k sine theta now as some k prime, for example, then you immediately see that this is just like a Fourier transform of the boxcar function for this slit, and that immediately can be integrated, or you could have integrated it anyway, but in this case we know that the Fourier transform of this guy over here is a sinc function, and then of course to calculate the intensity we square it, so I of theta then is proportional to sine beta over beta whole square. So hopefully this is all stuff that you have seen before, but just pointing out that when this happens, this just tells us something which is going to be helpful when we think about things like resolution and how much we can focus a beam. And the point is that any beam that has a finite spread or a finite width, right, or any if you have any optical system and the lenses have a certain diameter, for example, this says that after they go through that lens and have a finite width in the x or y direction, that immediately leads to a spreading of the beam after some distance L. Okay? And so the beam after some distance will have some spread, and you can go the opposite direction also. Right? You can see that you cannot focus the beam down infinitely small. Okay? So the first minimum of this will occur when for example, this first minimum occurs when sine theta minimum is equal, minimum here is equal to plus or minus lambda over d. So you can see that lambda over d plays an important role It is the ratio between the wavelength and the diameter of the slit. For a circular aperture, the formula is very similar. Again, it has a slightly different pattern there, but it's not a sinc squared function, but it's some Bessel function. But the point is that in the end, the sine theta is also roughly lambda over d, where now d is the diameter of the slit. So now that we know about diffraction, we can also think about interference, right? So in interference, there are two types of interference that we can consider. One is, we might call that temporal interferometers, or path splitting interferometers. And the classical example of that is the Michaelson Interferometer. And the other type, which is the spatial interferometers, or what we call wavefront splitting interferometers. And the classic example of that is the Young's double slit. So everybody has probably seen the Michaelson Interferometer, but I'll just quickly remind you what it is. Again, this will be very important when we think about correlations and also about quantum information processing with photons. Okay, so the Michaelson, and that's usually the only one that we'll consider in this course. We only have to worry about spatial coherence for very specific topics. Okay, so when I need to, I'll introduce it. But you can think of them from this simple categorization with these categories, temporal and spatial, that the Michaelson is going to tell us about temporal coherence of the electric field, and the Young's double slit is the way in which we measure the spatial coherence of a electric field or a light beam. Okay. So the Michaelson interferometer, you have a input electric field E in, which goes into a beam splitter, which is say 50-50, and that goes to a mirror and reflects back, and then here we have another arm, which is another mirror, and that also reflects back, and the distance from mirror 1 and mirror 2 is L1 and L2. These are two mirrors. Beams reflect back and then they recombine. Obviously there will be some beam going out this way, but we choose to look in the output port, which is down here. Okay? Then, and so there's an electric field out here, E out, which is E1 plus E2. Okay? And since the two arms essentially only differ in the path length, okay, we don't worry about the time evolution because that's just going to average out. So clearly, the difference in the path lengths leads to a phase which is dependent on L1 and L2. In addition, we might have some phase shifts, for example, depending on the type of beam splitter that we use, whether it's a half-silvered mirror or dielectric beam splitter, you can have slightly different phase shifts. Due to the beam splitter, there could be phase shifts due to the mirrors themselves. Depending on the polarization state of the beam, you could have some other phase shifts because of something inserted in the path over there. So all of these we put into that delta phi, and then this just becomes half E naught e to the I 2k L1 times 1 plus the I 2k times delta L times e to the I delta phi. Okay? So delta L is the path length difference between the two arms, and this gives rise to a fringe pattern at the output beam. For example, if we slowly scan the mirror M2, then you will see bright and dark fringes at the output port of your Michaelson interferometer. Okay? And so the maxima, for example, assuming this is, so you're going to get maxima of this pattern. You can calculate the so delta L here. Delta L is L2 minus L1, and delta phi I already told you about. So the maxima of this interference pattern will occur when 4 pi over lambda delta L plus delta phi is some integer multiple of 2 pi, and then the minima will occur when the same quantity, which is the path length difference plus the phase difference, is equal to some odd multiple of phi. Okay, so that was just a quick summary of interferometers. Now we can consider coherence, which is obviously an important topic when you're thinking about quantum information, as you see later on as well. So the basic idea of coherence is that if you have a sine wave or a cosine wave, right, sine omega t or sine kx, then we know that if we know the phase at some point, let's say this is z, or if this was time, let's say time, then if I know the phase at this point, t1, and this is a perfect sine wave, then I immediately know what will be the phase at some other point, t2, right? If the phase here was, say, close to 2 pi, right, somewhere near 2 pi or whatever it is, then we know immediately if I take some other time t2 later, which is given by the number of cycles that we can fit in there, we know that, let's say, the phase difference here between these two is well defined. Okay, if you have a perfect sine wave, right? Everyone okay with that? But if I now have a sine wave which for some time has one frequency and then suddenly shifts to another frequency, okay, now it becomes harder to predict what the phase will be. The amplitude of the wave, which is proportional to the phase, will be at some other point t2. Okay? And now imagine that instead of just one or two waves that we are changing or fluctuating like this, we have a large number of such frequencies, right? So if the source of light or whatever radiation that you're considering does not have just a single frequency omega naught, but has a bandwidth delta omega, omega naught plus or minus delta omega, then it means that we don't know, or we can't understand what the phase will be at some time later if we know the phase at time t1. It will be hard to predict what the phase will be at some later time. And that's all there is really to this idea of coherence, at least in this regime, which is the first order coherence, as I'll define in a moment. So so basically any realistic source, even a laser, has range of frequencies. Which we can encapsulate using some bandwidth delta omega. Okay? And the fringe pattern of, say, a Michaelson interferometer is in fact very sensitive to this bandwidth, because if you have one frequency omega 1, which has a corresponding k1, right? Remember, k's were proportional to the, or if you think about it, the frequency and the wavelength are related. So if the wavelength is lambda 1, then you have a maxima, but then if you have some other lambda 2, which has a minima at the same position delta L, then the two fringes overlap, the maxima and the minima overlap, and the contrast of the fringe pattern will vanish, right? Because earlier you had a very clear maximum and then a very clear minimum, right? And now the minimum from lambda 2, the other wavelength, is going to overlap with the maxima of lambda 1, or the other way around, whichever way you want to think about it, and that is going to end up causing the whole fringe pattern to no longer have a clear up and down maxima, minima pattern. Okay? So this leads us to define something called the temporal coherence. Tau C, okay, which, as you can see, is sort of a time over which the phase duration or the phase of the waves remains stable. Okay, for a sine wave, tau C is infinite, right? If it's a perfect sine wave, tau C, the coherence time, is infinite, because if I know the phase at this point t1, I can predict the phase at any point t2 down the line. Okay. But if it consists of some range of frequencies delta omega, then you will see, or you can probably guess, that tau C will be proportional to 1 over delta omega, the band. Okay? So it's a time duration. I'm not proving these statements. These are all, things that you can look up in any sort of optics book. We can also define something called a coherence length, Lc, which is just simply C times tau C. And what this implies is, of course, in a wave, right, you can interchange between the propagation distance and the time by simply multiplying by the velocity. So this is the coherence length. And that also can be understood from the Michaelson interferometer, because remember, this Michaelson interferometer, essentially you obtain an interference pattern by scanning the path length difference between the two arms. So the coherence length now in the Michaelson you can think of as the path length difference that allows you to maintain a sharp fringe pattern. Okay? And once you go beyond that coherence length, okay, once the delta L exceeds Lc, right? So if delta L exceeds Lc, the fringe pattern gets washed out. Okay. And if delta L, especially if it's much greater than Lc, if delta L is on the order or lesser than Lc, you see a fringe. Okay? So that would be the operational definition, if you like. Like if you want to measure the coherence length of a light source, this is what you do. Okay? You take the light source, you send it into a Michaelson interferometer, and then you see over what range of path length differences on the Michaelson you can observe a sharp fringe pattern. And that tells you the coherence length of your light source. Okay? And then once you know the coherence length, you can calculate the coherence time, tau C, simply by dividing by the velocity of light. There may be a 2 factor here. Okay, that's an important. Okay. Are you clear on this? This is an important concept. Any questions? Yes?
It's just like the concept confused.
Yes.
Here the delta omega is a range of frequency, which means like it should be like multi-frequency.
Yes.
Right? Like,
correct.
Like it can be like lots of different frequencies, but still in this range. It will be okay.
So what I'm saying is, if you look at the spectrum of this frequency source, right? Of the source, right? It may have some spread, okay, which is given by delta omega. Okay? For a white light source, this will be like flat over a large range of frequencies. Okay? For a laser, it will be very, very narrow at some one frequency, omega naught. Okay? And there are various in-betweens. For example, an atomic line from a discharge lamp is probably one of the best light sources we have in terms of the coherence length, right? Because it's extremely narrow frequency range. Unfortunately, it's usually very weak, so it's hard to do things with it. But in the past, when people wanted to do interference experiments carefully, or even if you go into our undergraduate optics labs here, if you want to do a careful interference experiment without a laser, that's what you do. You filter out the atomic spectral line, and you use that in your interference. So, for example, with a white light source, if you just took, like, for example, white light source like that, this is the reason why you don't see interference patterns all the time, right? Is that the white light source has such a broad frequency range that it essentially gives you like femtosecond type of, so you have to have, you can get interference, obviously, like from sunlight we see interference patterns all the time on the road, right? If you see some oil slick or a film, you can get an interference pattern. That's because the path length difference between the waves there is less than like microns, okay? That's typically what you're going to need if you want to see interference patterns from those kind of broad sources. But it is possible, right? Okay, and now that lets me define the first order correlation. Another way I like to think about these things is just analogies to random processes that we are all familiar with in nature, right? So for example, take the weather or the temperature today, okay? If you look at the temperature today, right, it's 25 degrees Fahrenheit outside, okay? And even if you didn't know much about physics or just knowing the nature, having lived on the earth for so many years, you know, if the temperature right now is 25 degrees Fahrenheit, most likely in a couple hours, it will be somewhere around either 20 degrees Fahrenheit or 30 degrees Fahrenheit. It's not suddenly going to become 100 degrees Fahrenheit. Okay? So we have a correlation time for the temperature, right? Or a temporal coherence of the temperature, which is a somewhat random variable, right? We know that over a time scale of a few hours, we can predict quite well what the value of the temperature is going to be. Okay? Now we're not so sure about tomorrow. It might be that tomorrow is way colder, right? Maybe it's going to be 10 degrees Fahrenheit. Okay? But again, it's probably not going to be 100 degrees Fahrenheit. It's probably not going to be minus 50 degrees Fahrenheit. So you start to see a decay of sort of your knowledge or understanding of the temperature as the time scale keeps increasing, right? And within like a few days, now our knowledge goes pretty quickly to zero, okay? Again, we can put limits. We can say it won't be 100 or minus 50 in Pittsburgh, right? Okay. So this is an analogy to what we are trying to do with correlation functions in the electric field, for example. So what we're going to do is right away just define the first so now it will be a task of figuring out which order any of this is. So the first order correlation function exactly uses this intuition about our ability to predict the value of the electric field over some time duration. And the way we do that is by considering the variance of the electric field, right? Because it's a random variable, okay? It's going to have some mean value and some fluctuation. Okay, and the fluctuation is determined by a sort of variance of the electric field. Okay, and this variance depends on the time, right, which we are going to encapsulate by this function. Okay, where this numerator is the time average over some long time interval t compared to, say, the frequency of the light. You'll notice that my g1 of t does not, tau does not depend on t itself. Okay, the reason for that is I expect that with these the type of waves or electric fields that I'm going to consider are what we call stationary, meaning that the origin of the time axis does not matter. Okay, so I'm going to set t equal to 0 here, or t equal to 100 seconds or whatever, and as long as we are measuring over some time intervals that are large compared to the frequency, there will be no difference between this value of the correlation function or the value of the electric field, this product, when it's time averaged in this way over with time t. Okay, does that make sense? Right. So basically, this is between, say, that's the, I guess, the full definition if you like. Right. And the reason it's a first order is because this is a correlation in the first power of the electric field with the first power at some other time t. Okay? And obviously you can generalize this to second order and higher order, and we'll get to that when we discuss quantum optics. Okay, if now let's take a simple electric field. I'll just write that formula here. Let's take E of t is some amplitude E naught times some frequency omega naught times some phase phi of t, which can be now thought of as a random variable. Okay. And as I was just explaining to you, the effect of like having multiple frequencies in your wave train, right, is sort of like having the phase of the wave fluctuate over some time duration. Okay, and that I'm encapsulating in this simple model as some phi of t, which will be a random variable. Okay, then we can calculate g1 of tau. I'm not going through the calculation, which will be e to the minus I omega naught tau times, sorry, I ran out of space here, some time, now this is going to depend on this random phase that I wrote in there. Okay. So you can see that this correlation function, the first order correlation function, is going to oscillate at a frequency omega naught, just like the original wave. And then it's going to have something here, the real part, let's say, of this is going to have something which is going to, as we'll show, will have some envelope that determines the coherence. So this is the oscillatory part, which you expect, and then this is the envelope that determines the coherence time. Okay? Again, I can assign some of this later, but let's just think of some simple properties that we can understand right away. which is that G1 of 0 must be 1. Right? Pretty straightforward. When tau equal to 0, then this cancels out. So G1 of 0 has perfect value 1. Right? Modulus. Right? I'm not worried about the phase factor. That's just going to always be. The second thing that you can see, that if tau is much smaller than the coherence time, tau c, then we know, as I was just saying, we know the phase is going to be roughly equal to the original phase. Okay, or will not be very far away from the original phase. And then when we time average this will still be roughly 1. So for tau small, much smaller than tau c, we expect that this G1 of t will be close to 1. Okay? And then as tau becomes greater than tau c, the coherence time, then phi of t plus tau and phi of t, which are random variables, are going to be very different from each other, right? Or they're going to be some large spread, and this is going to just average away to 0. Okay? So the simple physical picture of this then is, for tau far lesser than tau c, we expect G1 of tau to be close to 1. For tau far greater than tau c, G1 of tau is going to be close to 0. And you can think of that as just the effective result, that the time average of some random process, phi, delta phi, in this case the phi phase difference, the time average of some random variable which fluctuates rapidly because of the e to the I, which is a cosine function, is going to oscillate rapidly between +1 and -1, and that's going to go to 0, right? So we expect that if we looked at a plot of, say, the real part, or maybe the modulus of G1 of tau, but let's look at the real part for a second, then of course it goes between +1 and -1. Modulus is always go to +1, and it's going to oscillate at first and then slowly damp down to 0. Okay. Okay. And the time scale over which this is going to happen, roughly, right, is tau c, the coherence time. I'm just intuitively drawing this, right? We can prove all this. So, for example, and this is I'm stating without proof, if the light has a Lorentzian line shape in frequency, so everyone knows what a Lorentzian is. Basically, if I look at the frequency spectrum, the power spectrum of the wave or the electric field, let's say, of this light beam, and it has some Lorentzian line shape, okay, which is going to go as 1 over omega, this is omega naught, omega minus omega naught whole squared plus some gamma squared over 2, where gamma is the decay time or the decay rate. Then this Lorentzian line shape with a width, let's put that as delta omega squared over 2, then you'll find that G1 of tau is equal to e to the minus I omega naught tau times e minus where Tc, the coherence time, sorry, tau c, is equal to 1 over delta. Sorry. Got a little scrunched up there. Can everyone read it over there? At the end there? Basically all I'm saying is that G1 of tau for a Lorentzian line shape is an exponentially decaying line shape, coherence time. Okay, so there's an exponentially decaying correlation function, and the decay constant or the decay time of this exponential is simply 1 over the bandwidth of the Lorentzian wave function, delta omega. Is that clear? Again, no proof. It's just I'll maybe give you some homework problem on this. It's not too hard to show. And then, if you have a Gaussian line shape, so now instead of Lorentzian spectrum, if you have a Gaussian spectrum, then G1 of tau will turn out, again it has the minus omega naught tau, but then it has a Gaussian decay of the correlation function, where tau c, the coherence time, is just related through some constants once again to delta omega, 1 over delta omega. Okay? Again, no proof, but it's not too hard. I'll give you the basic understanding of this homework. Okay, so now I told you about the definition of the correlation function. I've told you how it's calculated in theory. You can ask, how do you measure it, right? Because in real life, you may have light with a Gaussian line shape, you may have light with some other line shape. You don't know what the line shape is. You want to determine it. Okay, you want to determine the coherence time, and you want to determine the correlation function. Okay, I already told you what the coherence length was. What is the coherence length? How do I determine that? We talked about it. What? How do I find the coherence length?
C times tau.
C times tau, but I don't know tau. How do I measure it? Michaelson Interferometer. Very good. So in the same way, using a Michaelson Interferometer, I can also measure the first order correlation function. Okay? So measurement or measurement of G1 of tau. The idea is that in the Michaelson, we know E output at some time t is 1 over root 2 E of t plus E of t plus tau, where tau is simply 2 times L2 minus L1 divided by C. Okay? Right? That is the Michaelson Interferometer expression. So from this, if you calculate the intensity for the output field as a function of tau, and as you can see, we can vary tau by using this path length difference, then I out of tau is simply going to be proportional to this, because that's just the intensity of the beam with time average of at the output port. Okay, and then you can substitute in for E out from this guy, right? E of t and E of t plus tau. Substitute that and you'll get, pretty straightforwardly, just carry out the algebra, that this I out of t is going to be proportional to some 2 I naught times 1 plus the real part of G1 of tau. Okay. Just from the definitions we already had for G1 of tau, you can easily show this problem. Okay. So this says that when G1 of tau, for example, is +1 over here, right, you're going to get 4 times I naught, which is what you expect. The 4 factor from the intensity has factor of 4 in front of it because there are 2 amplitudes that are adding up constructively. And when G1 of tau is -1, right, over here, then this is going to have destructive interference. You're going to get 0. Okay? So if the amplitude of G1 of tau is exactly +1 and -1, which will be close to tau equal to 0, then you get perfect visibility of the interference pattern. The interference pattern goes from 4 I naught down to 0, right? But then as G1 of tau starts to decay away, now the interference pattern, the visibility of the interference pattern is no longer going to be perfect. So by calculating the visibility or looking at the visibility, in fact, the visibility is defined as V equals I max minus I min divided by I max plus I min. You can easily show that this will be exactly proportional to this G1 of tau. Okay. Sorry, modulus. Okay, that concludes sort of a review of classical optics, and we have introduced now your first correlation function. This is the first order correlation function, and that also brings into light the important concept of coherence, or first order coherence as we call it now, because as you can see it was proportional to the first power, and I've shown you how to both theoretically define it as well as actually experimentally measure it in the lab. Okay, if you have a light beam, this is what you would do. And you can do this for other frequency regimes also, for example, if you want to calculate these things. In certain frequency regimes, some of these measurements can be very easy. In others, they may be hard. Okay. Any question? You have a question? Okay. Any questions? There are some powerful theorems about the relationship between this G1 of tau, which is also called the autocorrelation function for the electric field, and the power spectral density. Remember, we were just talking about this power spectral density of the electric, the spectrum of the electric field, and the power spectrum of any light field is very intimately related by a Fourier transform relationship, essentially, with the autocorrelation or the first order coherence function. So by finding the first order coherence function, you are also implicitly calculating the power spectral density of the electric field, especially, for example, with some random variable or some random electric field. Then this is a very important piece of information that you may want to have for any kind of calculations, simulations, etc. Okay, now since we are almost out of time, I thought I would now tell you something that I promised in the first lecture, which is to try and understand when it is that we really need to worry about quantized light fields. Okay. Or what you could think of as the difference between classical, semi-classical, and quantum, fully quantum optics. Okay. So to do that, I'm going to consider a box. This box is the whole universe. Okay? And so let's imagine that the whole universe is just made up of atoms at various points, and each of these atoms is emitting electromagnetic radiation and absorbing it, and so on. So there's electromagnetic radiation in the box. You can think of the box as just having some normal modes, right, which satisfy the boundary conditions in the box. And each of these normal modes behaves like some independent harmonic oscillator that is coupled to the atoms, and so everything reaches some kind of thermal equilibrium after you let it sit for long enough. Okay. So now the electromagnetic field in this box is going to be given by, again, I'm just skipping a lot of stuff that you all know already, but I'm assuming that it is some normal mode wave function or shape. There may be some extra shape due to the exact conditions of the box and so on, but it is going to have some relationship which looks roughly like this, times some unit vector E hat, which defines the polarization. And then V is also going to be related to this E naught. We already saw that relation, so I'll just write down the answer, which is it's just E naught times divided by C times K cross E, as we know, times sine K dot R minus 1. Pretty simple. Now let's look at the energy per unit volume in this box, which we can obtain from the Poynting vector or the intensity by just considering some volume of the box and using the intensity to find then, which is the unit per unit area, and then multiply by C, which is the distance that the wave can travel in any given instant of time. From that, or from other considerations of Maxwell's equation, we can immediately write down this formula, right? And then time average, okay? Right? That's just the volume density, energy volume density, epsilon naught E squared in the electric field, and this is epsilon naught V squared times C for the magnetic field. Okay, so then in a couple of lines of algebra, you can easily show that this is going to be related to this E naught by this formula here. Let's see, epsilon naught E naught squared, right? So we can ask ourselves, when will this energy density in this box when do we need to start worrying about this having a quantum behavior? Okay, the answer is pretty straightforward. When the energy density in this box starts to approach, or the energy in the box starts to approach that of a single quantum or single unit of energy of this harmonic oscillator that we have sort of thought of as the electromagnetic field, which is that when h bar omega, which is the quantized unit of energy, is approximately equal to this guy E naught squared times V, the volume of the box. Okay? These factors of half and so on don't matter too much. If I made a mistake there, we can fix it, but it's really not important for what I'm trying to get to here. Which means that the field of a single quantum of this electromagnetic wave is going to be simply square root 2h bar omega divided by epsilon naught times V. And this is the most important result over here. Okay? This is all we really need to worry about. And you're going to see this come up again and again when we do the fully quantized version of the electromagnetic field as well. This ratio h bar omega divided by epsilon naught times V. Okay? That and the square root, of course. That determines sort of the electric field of a single photon, which is a single quantum of the electromagnetic field. And this is the answer to a question that you might have wondered, what is the electromagnetic field from a single photon? That's this expression right here. And this V, of course, remember, was some box that we had to choose to obtain the normal modes and the boundary conditions of the Maxwell wave equation. Okay? So that's the funny thing about photons, right? You need to sort of think about the box in which they're being put, or the boundary conditions, because they're a wave. So that's how boundary conditions can influence the behavior of the photons. So what is the volume of this box that we could consider. And we can also ask ourselves, and you can also verify by putting in dimensional analysis that what I've said is not wrong. It's the simplest thing you could have come up with if you wanted to predict the field from a single photon. So the question is, when is the effects of quantum effects going to be important? You can sort of see that by saying, when will the field from a single photon be very large? Right? If I make the field from a single photon very large, then we have to worry about the quantization of the electromagnetic field. Okay, we have to consider that each of the modes or each of these waves is actually composed of this quantum particles, photons, etc. And you can see, once I've selected frequency, or if you think about it as there are only two knobs here, omega and V. Right? That's all I have in this simple result. So if I fix the frequency, then the only thing I have left to alter is the sort of the mode volume, the volume in which I confine the electromagnetic field. What is the smallest volume that I could consider? Okay, obviously the smaller I make that volume, the larger I make the electromagnetic field. Can I make it 0? Can I make the volume of the electromagnetic field 0? No? See, why do you say no? What's your name again? I'm sorry, I forgot.
I'm Cindy.
Cindy, yeah.
Because that's going to be infinity?
Yeah, it will be infinity, and I'm saying, why can't it be infinity? Huh? Quantum limit. What is the quantum limit? We are already at the quantum limit. Heisenberg principle. Getting closer, yes. What does the Heisenberg principle tell me about this mode volume V? Have a minimum? Minimum. What is the minimum, or what is the fundamental sort of limit of this volume? Huh? Yes, the uncertainty, I agree. What is it? What is the uncertainty in a wave, if you think about it? In its position, for example. What's the uncertainty that I have for a wave in position space? By the Heisenberg limit, it is, or by some other de Broglie limit, or whatever you want to call it. What is the fundamental sort of fuzziness in a wave that I can't go below if I have a wave? Lambda, right? The wavelength. Wavelength is sort of the minimum size of the box that I could make it, confined to. Because it is a wave, right? I need to have some definition for that wave to oscillate, so to speak. Okay? So V then is roughly on the order of lambda cubed at a minimum, right? You can also look at it from the diffraction limit, right? The diffraction limit that I told you about earlier, remember? We said that we can't focus a beam down smaller than sort of lambda over d, where d is the diameter of your lens aperture or something like that. So leaving aside the d, which could be anything, it could be huge, but lambda is sort of the fundamental limit there of your size of the beam. Okay. Okay. So from this, then we can immediately write down E naught, this sort of fundamental quantum electric field. You can immediately solve for what this is going to be proportional to. I won't bother with the thing, but it will be proportional to, once you put in that V is now lambda cubed, and lambda is then proportional also to the frequency, right? So this is equal to C over F whole cube, right? F is the frequency, omega is also the frequency, 2 pi times F, right? So once you put all that in, you get, it's roughly proportional to F squared times H naught, H bar, epsilon naught C. Maybe it's H, sorry, whatever, okay, something. Okay, and we can actually calculate this. So for lambda equals 633 nanometers, which is a red laser, you get E naught is on the order of 367 kilovolt per meter. So that's the kind of electric field you would need for a wavelength of red light to get quantum effects. Okay. You need to confine this and make it really strong to get quantum effects from a single photon, from the light. Yeah, we can actually plot this, and you can also ask what is the classical limit. Well, I'm going to roughly say when the number of photons, the average number of photons, is say on the order of 10 to the 4, which means by short noise the fluctuations will be on the order of 10 to the 2, and that will be 1% of this sort of. So this is like a classical limit. So earlier I considered 1 photon, and I'm saying once I get past about 10 to the 4 photons, you can pretty much view this light field as a classical wave, and you'll see that that limit is then on the order of 10 to the, or 100 times E0. So if I were to plot this in a log scale, because as you can see, E0 is proportional to a power of the frequency f. Okay. I'm just roughly going to sketch it. Okay. So this is E0 average value versus f, the frequency. Okay. You can see that because of the nature of this f squared, it's going to have in a log scale, log f, log E0, then it's just going to vary by very big. I just plotted it using mathematical. I forgot to bring it in, so I'm just sketching it over here. And this is 9, 12, 15, 18, 21. So this is really like 10 to the 9 hertz, 10 to the 12 hertz, 10 to the 15, 10 to the 18, 10 to the 21 hertz, etc. So these are the frequencies on the x-axis, and on the y-axis is in units of E over E0. Sorry, E over E0. The fundamental amplitude over there. We see that we're going to look something like that. And then, as I said, we put this sort of. This is of course very rough, right? I'm just saying, if once the field exceeds sort of on the order of 10 to the 4 photons, you can think of it as classical. So that's, you can adjust that however you like, but you can see that that will create another sort of range over here. So all of this sort of you can think of as classical light over here. Okay, and this in this narrow regime here, so to speak, in this, I mean, of course, this is a log plot, so this is a huge orders of magnitude here. But in this sort of regime, this is where quantum optics lives. Where we're going to consider sort of, so at every frequency you can sort of see when do I have to worry about quantum effects of the light, and when can I treat the light as classical. Okay, and there's still some subtleties here. There may be situations where the light is interacting with an atom, in which case we have to take into account the quantum nature of the atom or the qubit, for example. But that's different from considering the purely quantized nature of the electromagnetic field itself. Okay, I'm well past my time, sorry. So we'll stop here. If you have more questions about this.